And without further ado, I'll hand over to Paul. Thank you.
Thanks, Chris. Okay, morning everyone, or afternoon now, sorry. Firstly, thank you for the invite, and looking forward to presenting to you the technology that we've developed, a new approach to closed loop real-time optimization over the next half an hour. As Chris said, I'm going to just give you some background to the technology, how it can be applied and the benefits, etc., and give you a quick demo. Hopefully we'll have 10-15 minutes at the end for any questions you may have. So just to introduce me and my background. So all my career I've been a process control optimization engineer. I started off as a C&I engineer really with BP. So I joined BP in 1988. I worked 16 years downstream on mainly chemical plants, and then 17 years on upstream assets around the world, working out of Sunbury in central engineering. The last role I held for the last 8 or 9 years with BP was chief engineer for instrumentation control electrical. So I was head of the discipline for instrumentation control, electrical measurement, etc. Those types of disciplines for BP. I'm also a visiting professor at Imperial College, which I've been since 2017. So BP allowed me a couple of days off a week during the summer term, actually, to lecture to students, undergraduates and postgraduates at Imperial as part of my role as chief engineer. So I taught process control, dynamics, optimization to undergraduates and postgraduates, it says there. I left BP at the end of 2020, after 33 years. I didn't certainly want to retire, still want to keep busy and still want to keep my brain busy. So I thought about long and hard what I was going to do, and I decided to focus on trying to solve a problem that had been bugging me for certainly through the latter part of my career with BP, namely how difficult applying optimization is to closed loop, to processes, advanced control to processes. So I developed a new approach, completely new approach, which I'm going to take you through today. What I'm calling an auto agent approach to real-time optimization. I started a company in 2021 called Ortomation Limited to basically commercialize the technology, and I've been working with a colleague of mine, Andrew Ogden Swift, to do that. So what's been my motivation? As I said before, the optimization provides significant benefits, but very few companies have taken advantage of it. Only the big oil companies, big chemical companies have really taken advantage of it, because it's difficulty to install, maintain, and then maintain. And I've always thought there must be a better way. You've got PID loops on a plant that control things to set points, reject disturbances, control, move to new set points. A good control engineer, even a good technician, instrument technician on a plant can tune a PID loop, build a control scheme. So in my view, applying optimization should be as easy as doing that. So I'm going to cover today what is real-time optimization's current state of play, what is our software and why is it new, why is it transformative. Look at existing and future marketplace for this, the status of our product, next steps, and give you a quick case study and demo. Hopefully it'll be interesting to you guys. So what is real-time optimization? Real-time optimization is basically you've got a set of manipulated variables. This diagram, just to visualize it in 3D, it's got 2 manipulated variables, but you could have n manipulated variables as long as they have a cause and effect on what you're trying to optimize. So your real-time optimizer will adjust set points on a plant, for example, and hopefully move your process to a better operating point to maximize or minimize something. So on a offshore oil and gas facility, you may manipulate suction pressure on your HP compressors, things down your liquid train to try and maximize oil production from the reservoir, for example. So typically the optimization variable is a proxy for profitability. So you say it's for maximize something, minimize something. Throughout the history of optimization, real-time optimization has been applied on plants really since the mid 1980s, probably earlier than that. And it's been shown time and again that the delivered benefits is between easily 2 and 10% improvement in what you're trying to optimize. Payback is measured in months, but it can be in days. You increase the production, oil and gas production for an offshore facility by 2%, then you're talking days, not months, in payback. And the existing market size for this technology is about, I don't know, 0.5 billion to $1 billion a year around the world. And there are two or three key vendors that sell you real-time optimization technology, and you probably know them. I'm not going to mention them, but you probably know them. So current state of play, well, there are lots of ways of applying real-time optimization technology, and I've got 6 buckets here, and you can put the technology in one of these six buckets. But all the existing technologies have been very successful, but only when expertise exists and when you can afford it. The companies have the dollar resources to buy the licenses and also then maintain it over time. And the applications, therefore, need to justify the expense and the aggravation in building them as well. So very limited market. So it's dominated by these types of solutions in the red bucket. Sorry, the blue buckets. But they all have one thing in common, and that's a deep dependency on needing a high fidelity model on which the optimization algorithm uses that model to provide the answers to where to move over in real time to the optimum location. So making schemes difficult and laborious to build, reliant on specialized scarce resources. Also, because they're more reliant on models, you're then the optimization is only as good as the model you've built, so you're prone to model error. And as I've said, they're costly. And these are the reasons why only the big companies with lots of resource, lots of applications that can justify this technology have invested in it. Traditional RTO, as I've described it, is therefore often ruled out or never considered because of the expertise required. And sometimes, and I found this in my career, even if you spend a lot of time building these things, these real-time optimizer advanced control on processes, over time, if you don't maintain them properly, because the process deviates away from the model you've identified, that process model mismatch degrades the real-time optimizer performance over time, and eventually they're switched off. So not only have you got to invest heavily to install the thing, you've got to invest heavily to maintain it over time. As I said, the market is between $500 million to $1 billion per annum. But we estimate, we've done a lot of research into this. A colleague of mine, Andrew, has done a lot of research into this, and he thinks that because of these limitations and because of the expense, only 10% of the possible market is being served by optimization. So what's our target market with our technology, which addresses these shortcomings? Well, we're targeting industrial sectors, applications where traditional model-based solutions have been overlooked, ruled out, or failed. So where there's a knowledge gap, lack of expertise, or costs are too high. And as we say, we believe that's about 90% of the applications around the world on all types of process plant, be they power, pulp and paper, fine chemicals, whatever. So outside the traditional oil and gas, bulk chemical type businesses, industries that real-time optimization is heavily invested in at the moment. So what is our technology, ORTO? Because having a model is the biggest obstacle to implementing optimization, we've gone down the model-free approach. And we've designed the technology around agents, and I'll talk you through that in the next slide. And these agents reside in the DCS or SCADA system, either at the application layer, the DMZ layer of your DCS, or actually in the future potentially in the control layer as part of your control suite, control libraries within your SCADA DCS systems. And essentially, our mantra has always been make the application of optimization as simple as PID. So hopefully I'll convince you today that our technology is simple to configure and deploy. It's self-learning, autonomous, but it's not artificial intelligence as the way people are marketing AI at the moment. And they work together to find and then track the optimum over time. That's important. So if you're this animation here, so if your optimum moves from this point, if you can see my mouse, to this point over time, then our technology will track that because it's model free. It's just adjusting, continually trying to hunt for the best solution. If that solution moves, it will track and follow that optimum movement. So a new approach. So how is this implemented? Very simply, schematically, traditional optimization schemes are set above the PID layer in a DCS, and they write down to a set of set points. So I've got 4 manipulated variables here: an analyzer controller, pressure controller, flow controller, and temperature controller, right down to the PID layer. And as I've already talked about, building these things to optimize your process by manipulating these set points. I've shown 4, but there could be 20, whatever your process needs. Is difficult because of the dependency on scarce resource. They deteriorate because process model mismatch increases over time, etc., etc. So what have we done? We've taken a completely different approach to this, and so we have got what we call auto agents, and for every manipulated variable, it has its own auto agent in a cascade, like a primary, secondary PID cascade loop. We have a cascade system where each auto agent writes down to its manipulated variable to optimize the process. And those auto agents, even though they're autonomous and are basically built like cascade loops, they work together to achieve the optimization objective function. They all work together to maximize or minimize your optimization variable against a set of constraints you defined. So essentially what we've done is make the design of your optimizer or optimization scheme as simple as PID, because building these things, as I'll demonstrate later on, is simple, very intuitive, they're robust, standardized and scalable, and because they're model free, they require minimal amount of maintenance. From a project standpoint, I've been very conservative here, but the traditional RTO timeline is usually months to build these things and months to commission them, and they usually go overrun in time for various reasons. So I've said, a typical RTO scheme could take 3 months, usually a lot longer than that, to commission and monitor. And that the big building block in that timeline is actually the time spent to identify or build your model from first principles. And then use that model to build your optimizer. Whereas our approach, because it's model free, you don't need to do that step, and these auto agents are a lot easier to build and commission. Then we believe our technology reduces the timeline to build these schemes by at least 70%. I'm again conservative at that number, and because you're not having to maintain a model over the lifetime of your plant, if you want the optimizer to run over the lifetime of your plant, we believe there's about a 90% reduction in the amount of maintenance required on the model. So key milestones achieved. Getting back 3 years ago now, we did a proof of concept with R&D software. We built our auto agents in MATLAB Simulink originally with R&D software, and we applied our technology originally to an optimization problem on a oil refinery, and it was chosen a digital twin of an oil refinery, I should say. It was chosen because traditional techniques had failed to solve the optimization problem, so it was an ideal task for us. And the traditional techniques had failed because the dynamics of the process changed significantly over time for various reasons, and we showed our technology wasn't susceptible to that and succeeded where traditional technologies had failed. So based on that, we said, right, okay, based on that great success, we then spent a year and a half developing our software, which I'll take you through a quick demo in a minute of. And we've tested, this is a standalone application for the software that sits at the application layer of your DCS. And then obviously that software has been tested to death really on numerous problems, benchmark studies, processes, chemical processes. We've even applied it to wind turbines and maximizing power from wind farms, and various other applications for real-time optimization, all using digital twins of processes. And lastly, about a year ago, we engaged a third party, a company in Scotland, completely independent of us, to take our software and test our software against benchmark optimization problems. And the two benchmark optimization problems they chose were an anaerobic digester reactor, so basically producing biogas or methane from a organic material and maximizing that with an optimizer. And some of you may have heard of the Shell heavy oil fractionator problem, which is a sort of like a problem that Shell came up with in the 80s, 90s for testing advanced control optimization. So they applied it to that. So all success criteria that we set out initially were met by the third party. Needed minimal training for our engineers to build these things. I think I gave the engineer that built the optimizers just 2 hours training. They then went away and built the schemes very, very quickly. The constraints they laid down were adhered to. The true optimum found was tracked, and they confirmed that software was intuitive. They've written a report, which is, if you contact me, if you're interested in seeing how they tackle these problems and their results, then please send me an email, and I'll gladly send you the report they wrote on the testing. So those are the key milestones achieved. I'll just quickly take you through an example. So our technology not only can be applied to process plant, chemical plants, oil and gas facilities, power plants, whatever, wind turbines, whatever, any complex real-time process, because it's a generic optimization tool. It can be applied to other things as well. And what I thought was this example, given the audience today, this would be an interesting example for you guys, basically using our technology to auto-tune a PID controller. So you've got a PID controller that's in a classical single in, single out closed loop. So you're trying to use the PID controller just to reject disturbances and control to new set points, this process. And I said, okay, let's apply our technology to this, and say this process, it's dynamic. Sorry about the equations. These are Laplace transfer functions. Don't worry if you've not covered Laplace in your dim past. But basically, what we've got is a process that changes from a second order process with time delay, and then over 10 days it smoothly degrades or changes to a first order process with double the gain. So the time delay disappears and the gain doubles. So I'm using our technology, ORTO technology, to say, okay, given these changes in process dynamics, we want an auto tuner of this PID controller to keep the closed loop response constant. And I'm saying, right, okay, our desired closed loop response is just a first order of gain one, obviously, with a first order time lag of a time constant of 50 seconds. So the way to do this is we can apply what's called model reference adaptive control structure. Been around for a long time, this sort of structure, and we can say, okay, what we're trying to do here is adjust the PID settings in this control loop by comparing the closed loop response with what we want the desired response to be, and then minimizing that difference. So this adjustment mechanism is all about minimizing the difference between what we want the closed loop response to be to what it actually is, and adjust the PID settings to do that. We can I've got a simulation I can run if you're really interested. Again, I haven't got time today, but anyone interested, I can just run through the simulation. But taking this structure, we can apply our auto agents as the adjustment mechanism in this structure, and have 3 auto agents, one adjusting the P proportional, one adjusting the integral, and one adjusting the derivative. And we're basically saying, oh, right, okay, the objective function is to minimize some performance indices, which I've basically integrated time absolute error, basically auto tune this PID controller to meet our desired closed loop response, and say, right, okay, initially it's really poorly tuned with a poor, very low gain, low integral action, and low derivative action with an ideal PID controller. So these are results you get with applying our technology. So this is, as I said earlier, the process dynamics change over 10 days. So these are the closed loop responses after 0, 3.3, 6.6, and 10 days. Here, this is the response with the initial PID settings, which you can see is pretty bad. So initially, the auto agents, these are the adjustments to the P, I, and D by the auto agents. You see initially the auto agents are adjusting these P, I, and D parameters to achieve your desired closed loop response. And this is how the auto agents adjust those parameters over time to maintain as closely as possible the desired closed loop response. So we've shown here that our auto agents can not only be used to optimize plant, but it's be used to optimize the P, I, and D settings in a PID controller to meet a desired closed loop response. So I've gone through that example very, very quickly, but again, if anyone wants any further details or a demo, please get in contact. Okay, current status, where we are with the technology. Well, we've been following obviously, because we're a startup, we've been following the technology readiness ladder. We're at the end of level 6, if you like, now, where we've been done all the testing and development work, and now we're moving and we're seeking to work with a partner to gain reference sites. And if you guys are interested, any of you are interested in looking at this technology for an optimization problem that you have on one of your assets or plants, then please get in touch. We'd love to work with you. All the work would be free of charge, just to show that we can apply our technology on a real plant. So that's where we are in terms of technology readiness. The pathways for implementing it. So this is the standard sort of architecture for a DCS SCADA system, if you're familiar with DCS systems. So our intention is that our software will reside in an application server at layer 3, and then communicate with the controller down at layer 0 through an OPC server. So our software uses OPC DA and UA to communicate with the controller down here to optimize the plant, or drive set points and optimize the plant. In future, if and when we partner with a control system vendor, we can put our auto algorithm in the control system library down here. So when you're building a DCS or building a control scheme, you can build an optimization layer or optimization scheme at this layer as well, and the controller layer as well. So that's how it's implemented on a DCS. As I say, this one we've done and developed. This one is future, and hopefully will be done in a year or so's time. So software, I won't go through these screenshots. I'll take you through a demo now. So hopefully you can still see the demo, see my desktop. But this is the software. I've got it running at the moment just to optimize actually the power generated from a wind turbine, which is a really interesting optimization problem. But that's an aside. Essentially, for every instance of our software, you can apply one optimization scheme. So if you've got 10 optimization schemes on your plant, then you have 10 instances of this software. So we've designed the software to be as intuitive as possible. So working from left to right, you put your license number in, accept the T's and C's. Then you build your OPC comms, either using UA or DA. For this particular example, I'm using OPC UA. And these are the signals I'm reading in and I'm writing out to. Then you build your optimization objective function, what you want to maximize using what I've got 3 MVs in this particular case. I'm writing down to 3 MV set points here. What's my constraint? I've got 1 external constraint here. And what we use pause logic, what we call pause logic, to back initialize the auto agent. So if the secondary PID loop isn't in the right mode to receive the set point from the auto agent, then it will back initialize based on a pause flag logic. Then you build your agents. So here I've got 3 agents running. So you just, as I said, these things are as simple to build as a PID loop. So this agent is manipulating rotor speed of the wind turbine. You set these parameters, configuration parameters, just a few configuration parameters to set, and then you let me put that. I've had it running for about 24 hours, I think, something like that. Yeah, so this is how it's adjusting the tip speed ratio to maximize the power generated from the turbine. So this is the PV or the MV moves, and these limits are the boundaries within which it can move the value. These red markers are when it's hitting the constraint line that you've defined for the auto agent. This is when it's been on, and this is when it's been paused. So yeah, configure that for 3 agents, switch them on, and just watch. Once you've switched the optimization or auto agents on, you just watch them work and do their stuff. So if I set this to 24 hours, this is what we're trying to maximize, the optimization variable, power generated from the wind turbine. You can see that this is where it's taken the power generated from the wind turbine up and maximizing it. I know this is around about 1940 with a bit of noise on top. Is where the maximum is. So it's done the job within a couple of hours of the optimizer being switched on. There's lots of tabs here to analyze the optimizer performance, which I can take you through. You can look at the various plots, constraint, pause, logic plots. You can plot how in 3D how 2 MVs on the bottom here, how they've been manipulated to maximize the optimization variable, which in this case is power generated. So you can see the over time, and these dots are a bit scattered because of the noise, the process noise on the power measurement. You can do cross correlation. You can do radar. This is quite good. Radar plots to determine how much each MV has moved to achieve the optimization. So you can see this one that on this plot, this used OA1, which is the optimization. I think that's that's the tip speed ratio. It's had to move that quite a bit to achieve the maximization. Anyway, lots of things here to analyze and determine how well your optimizer is doing. Lots of other tabs to look at, but hopefully that's it. That's how you build a scheme and monitor a scheme in software at the application layer on your DCS. Very simple, and everyone that's used it and everyone that's applied it on various examples, their instant feedback is that this is 100 times easier to implement than a traditional optimizer. It's easy, or some people say it's easier than building PID loops. So anyway, I've tried and I've gone through that very, very quickly, Chris, trying to leave some time for some questions. So back over to you. I'll see if I can get the so stop sharing. Chris, if you're there,
yes,
happy to take questions for the last 10 minutes or so.